Okay, today we're going to be talking about multiplying and dividing radicals and simplifying by rationalizing the denominator. This is sort of two sections in one. And here's a list of the examples that we're going to have in the video. Someone suggested that I do this, so this is in order, and it was a good suggestion, so I thought I'd go ahead and do it. And this is in order, so if you're looking for something in particular, scrub through the video until you can find what it is that you're looking for. Okay, so let's go ahead and get started. So the first thing we're going to talk about is multiplying and dividing radical expressions. Okay, so there are two important rules. And one of these rules that we've already talked about, it was the product rule. So if we have square root of x times the square root of y, that's equal to the square root of x times y. Okay, let's go ahead and put a 1 in front of it, just so we know that there are two rules. This is the product rule. Remember this from the last section. The next rule is very similar. It's called the quotient rule, and it is it actually basically is the same thing. It's just that we think of it in terms of fractions or dividing instead of multiplying. Whoops, okay, sorry, I mistyped it. Okay, so the square root of x over the square root of y is equal to the square root of the entire fraction. Okay, so both of these are really important. Remember that rule number 1 is the product rule. Rule number 2 is the quotient rule. We're going to be using them both quite a bit. So let's get started with the first example. So it's 2 times square root of 5 times 3 times square root of 2x. Okay, so 3 times the square root of 5 times 3 times the square root of 2x. Okay, so let's go ahead and... Whoops, I jumped way up too high. Okay, so... try not to make it too close to the edge there. Okay, so... this right here, we could take this 2 and this 3 and... well, let's go ahead and rewrite this without the parentheses, okay? Because since we're multiplying this all together, we don't need these parentheses, since the only thing involved in multiplication. So let's go to the next line, and we'll say 2 times square root of 5 times 3 times square root of 2x. Okay, so let's make that a little bit more clear. Okay, because that 3 is outside the radical 5. We don't want the 3 underneath that. That's why I want to go ahead and make that clear. So now, since these two things, let's go ahead and put an equal sign just so we know that we're dealing with the same thing. Okay, so now that we have all these things are being multiplied together, we can rearrange them in any order we want. So let's go ahead and combine this 2 and this 3 to make 6. So this 2 and this 3 make 6, but then we have this root 5 and this root 2 6, and we can combine those two to make square root of 5 times 2x. Okay, so this root 5 times root 2 6 comes together to make this right here. So this 5 times sorry, I should say this 5 and this 2 will come together to make 10, of course. So we have 6 times square root of 10x. Okay, so now we have multiplied these two together, and that's what these two expressions together, and that's what we were originally told to do, is to take 2 root 5 times 3 root 2x. So, and we ended up with 6 times root 10x. Okay, so let's go on to the next example, and that's going to be negative 5 times the square root of 6 times 2 times square root of 3. Negative 5 times the square root of 6 times 2 times the square root of 3. So, let's go ahead and I'm going to go ahead and skip this step where we remove the parentheses, because we don't really, as long as we can see it, okay, we can see it, there's no pluses, there's no minuses, there's only multiplication. So we can go ahead and rewrite this as, we can take this negative 5 and this positive 2 will become negative 10. So this negative 5 and this positive 2, you multiply those together and you'll get negative 10. So then we have the negative 6, sorry, not negative, root 6 and root 3. Well, that's going to be equal to the square root of 6 times 3, which is going to be 18. So square root of 6 times the square root of 3 equals 18. Okay, so, but we're actually not quite done. And the reason why we're not quite done is because this root 18 can be simplified a little bit further. Remember, that was from the previous video. The root, whenever we have a number under the radical, we want to see, okay, can we simplify this number any further? If you don't check that, then you're not actually done with the problem. So 18, this can be written as the entire, let's go ahead and go with the entire problem. The entire problem can be rewritten as negative 10 times the square root of 2 times 3 times 3. 2 times 3 times 3. Okay, so we're talking about a square root, so there's an implied 2 here. So that means we're looking for pairs. And we have a pair of 3's right here. So we can go ahead and cross out those 3's. And put one of those 3's out in the front. Don't forget that you're multiplying. Okay, that line no longer belongs there. Okay, don't forget that you're multiplying the negative 10 and the positive 3. So this will become, on the next line, negative 30 times the square root of 2. Okay, did I accidentally... No, okay, this 2 is not being crossed out. Sorry, it's not too clear there. Let's just go ahead and get rid of the line. I'll just go ahead and... Oh, it doesn't matter. Never mind. So, bottom line is, this should be clear that the 2 is not being canceled, just the 2 3's. So this is equal to negative 30 times root 2. And this is going to be our final answer. Remember that once you're done multiplying them together, see if you can simplify this further. See, in this case, we couldn't simplify it further because you're going to have 2 times 5, and you can't. There's no pairs there. But in this case, in 18, we had a pair of 3's that we could pull out to the front. So we have negative 30 times root 2. Okay, let's go on to another example. So we're going to have 3 root 3 plus root 5, all of that times square root of 3 minus 2 square root of 5. Okay, 3 times the square root of 3 plus I'm sorry, let me start this over. 3 times the square root of 3 plus root 5, all times root 3 minus 2 root 5. Okay, so in this case, remember, let's go ahead and scroll down a little bit. In this case, oh gosh. Okay, so what we have here is essentially two binomials. I mean, I know it looks daunting, but this is actually ultimately, it's not very different from, let's say we have A plus B times C plus D. This is ultimately the same thing. It's just that you have this whole thing here is going to be your A, this 3 root 3. This is going to be your B, C, and D, except we've got minus, so the minus 2 root 5 is going to be the D, which means that we're going to be handling it the same way. So we're going to distribute these two, or if you want to be if you want to use the what's sort of the acronym, you can FOIL it. You know, first, outers, inners, last. Okay, so let's go ahead and deal first with the first ones. So we have 3 root 3 times root 3. Okay, so 3 times root 3 times oops. 3 times root 3, so yeah, sorry, 3 times root 3 times root 3, and that's what we have here. So then for the next part we have this is the inners. Now the outers is going to be plus 3 times root 3 times negative 2 times root 5. Oops, I forgot the parentheses. Okay, don't forget this negative because you have a plus, a minus right here, so it's like plus negative 2 root 5. So this, let's go ahead and clear this off. So this times this is equal to this. So this was the first right here, this was the outers. Now let's do the inners. So root 5 times root 3. So plus root of 5 times root of 3. So this root 5 times root 3, that's the inners. Okay, now let's do the last, root 5 times negative 2 root 5. So this is going to be plus root 5 times negative 2 times square root of 5. Okay, that's kind of long, but it's something we can still work with. So this is the last, root 5 times negative root 2 of 5. Okay, so now let's go ahead and see which individual terms we can simplify. Well, this is 3 times square root of 3 times the square root of 3. Well, what's the square root of 3 times the square root of 3? Well, by definition, the square root of 3 times the square root of 3 is just going to be 3. So this becomes 3 times 3. This 3 is this 3 right here, but this 3 comes from root 3 times root 3. Okay, so now we're done with this term. Let's move on to this one. Sorry, this one right here. So, whoops, I didn't mean to erase that much. I mean to mark that much. So, root 3 times root 3 times negative 2 times root 5. Okay, well, first let's go ahead and combine this 3 with the negative 2. And that's going to give us minus 6. So root 3 times negative 2 gives us minus 6. Now we could write this as plus negative 6, but it's going to be faster to write it as minus 6. That's why I go ahead and do that. So this minus turns this into a plus. I'm sorry. This minus turns this plus into a minus. So then let's go on to these. So that we're done with these terms, 3 and negative 2. We're done with them. Let's just I'm not crossing them out because they're gone. I'm crossing them out because I don't want to be distracted by these two. I'm done with them already, so I want to deal with whatever's left. So then we have this square root of 3 times the square root of 5. So that means we're going to have square root of 15. So square root of 3, so 3 times 5 is 15. So the square root of 3 times the square root of 5 equals 15. Equals the square root of 15. Okay, so now let's go on to this term here. Well, this is exactly what we were just dealing with here. I mean, except that now it's a little bit more explicit. The square root of 5 times the square root of 3 is going to equal the square root. I may have said 13 before. I meant to say 15. So the square root of 5 times the square root of 3 equals the square root of 15. Okay, so from here we get here. We come here. So now we have this term left over here. So there's only one non-square root term, and that's this minus 2. So we can write this as minus 2, and then we're going to multiply it by whatever is over here, whatever else is over here. Okay, so we're done with the square root of 2. Remember, I'm not crossing it out because it's gone. It's still here. I'm just crossing it out because I'm done with it. So I want to move on to these two. So square root of 5 times the square root of 5. Square root of 5 times the square root of 5 is just going to be 20. I'm sorry. It's just going to be 5. So from these two we get 5. So now this is our slightly more simplified version. We're still not quite done because we have this 3 times 3. I mean, it's a pretty obvious simplification from here. So we have 3 times 3 is going to give us 9, and then we still have the 6 times square root of 15 plus square root of 15 minus, and then this 2 times 5 is going to be 10. So now I want to go ahead and combine like terms. Remember, that was the last thing we did last section. And we're going to have this 9 and negative 10 is going to make negative 1, because 9 minus 10 equals negative 1. And then we're going to, so I'm going to go ahead and cross these out just because I'm done with them. So we have minus 6 root 15 plus root 15. Okay, so we have like terms. They're both root 15, and let's see if I can draw this without it looking too horribly messy. 15 equals 3 times 5. Okay, that doesn't look too good, but you can read it. 15 equals 3 times 5. And so that means there's nothing that you can cross out. So that means that this root 15 is as simplified as it gets. So so what we have here is like terms. We have negative 6 plus 1. So that's going to give us minus 5 square root of 15. And this is our answer. This is as far as, here, let's go ahead and clear the rest of this out. This is as far as it goes, because we can't simplify this any further. So now we went from here, up here, we went from here down to this, and this is a lot simpler. It makes a lot more sense. So let's go on to another example. We have 3 more examples, and then we go on to the next subsection, and that's simplifying radical expressions by rationalizing the denominator. But for now, let's go ahead and go on to another example. So, example. Let's say we have square root of 24 over the square root of 6. Okay, so let's scroll up a little bit. Okay, so square root of 24 over the square root of 6. Now, individually, this might be kind of complicated. I mean, what's the square root of 24? Well, I have no idea. What's the square root of 6? I have no idea. Those are both irrational numbers. But let's go ahead and let's copy this and put it on the next line. I like to recopy it sometimes. That way we know that we're on this line, we have more room to work with it. So remember from the quotient rule, let's go up to it, the quotient rule, that we can rewrite this as a single fraction. So not a single fraction, a single radical. So we have the square root of 24 over 6. Let me scroll up. I forgot that I had. Okay, there we go. So square root of 24 over 6. Well, what's 24 over 6? Well, 6 goes into 24 4 times. So this is equal to the square root of 4. And what's the square root of 4? Well, it's just 2. So that means that the square root of 24 over the square root of 6 is just equal to 2. And that's, well, obviously that's simplification, because 2 is a lot easier to understand than root 24 over root 6. So that means that this, in this case, obviously, you can't get any simpler than 2. I mean, I've never heard of anybody trying. So let's go to one more example. This one involves a cube root. Cube root of let's go ahead and make this. This is a separate example. Oops. Cube root of 1 over 64. Okay, well, remember from the quotient rule that we can rewrite this as cube root of 1. Yes, 1. Times the cube root I didn't do this right. I mixed something up. Here we go. Okay. This is equal to the cube root of 1 over the cube root of 64. So what's the cube root of 1? Well, it's just 1. Because 1 times 1 times 1 is 1. The cube root of 64 is actually going to be 1/4, because 4 times 4 is 16, and 16 times 4, well, that's going to be the same thing as 32 times 2, which is going to be 64. So that means that the cube root, if you have 4 4s, that gives you 64, which means the cube root of 64 is 4. So this is going to be the final answer for this simplification. And obviously this is a lot simpler. Okay, so one more example. This one's a little bit harder. I know the previous examples were pretty tedious, but now we're going into something quite a bit more difficult. Okay. The square root of 27 times 8 to the 4th over the square root of 64x squared. So this entire thing, let's go ahead and do the quotient rule. So we have square root of fraction of the square root of 27a to the 4th over square root of 64x squared. Okay, I did something wrong. Okay, the fraction of Okay. Yeah, sometimes this the code can get tedious. So we have the square root of 27a to the power of 4 over 64x squared. Okay, well, we can think of this two ways. We can go ahead and think of this as, okay, what's the square root of 27? Well, we'll leave that for later, and then the square root of a to the power of 4 is going to be a, and then we'll do the same thing here. This is just going to be ax, 8, not a, 8x. But let's go ahead and just go ahead and use the few individual rules. So this will be the same thing as a fraction of square root of 27 times the square root of a to the power of 4 over square root of 64 times the square root of x squared. Hope I didn't type that wrong. Okay, good, I got it up. So I can go ahead and separate this out, and you probably don't need to do this necessarily, but I only want to do this to show the individual rules. This one especially, this is going to be pretty easy. This is going to be 8 and x. So you can kind of see that it's going to be 8x from here. The only thing that's tricky is this 27 right here. Yeah, that's not. This 27 right here is going to be a little bit tricky. So let's go ahead and deal with this. This square root of a fourth is just going to be a squared, but then you're going to have the square root of 27, and then we're going to have 8x on in the denominator. So this a to the fourth is easy to deal with, but then we have this 27. Okay, so here you can do a factor tree of 27, and I went ahead and did this in a different program just to. So this is going to be, this is my cheap and dirty factorization of 27, and oops, I didn't mean to get rid of it, but so there it is. You can see that 27 is 3 cubed. So I'm going to go ahead and rewrite this as okay, so we have 27 is going to be 3 cubed, and that means we're looking for pairs, so we have one pair of 3's that we can get rid of. So let's go ahead and get rid of it. Well, not get rid of, but move to the front of the radical. So that means we can rewrite this as okay, we can cross out the 3's and move it to the front. I'm going to move it in front of the a squared. So we have 3a squared times the square root of 3 over 8x. And as usual, I want to go ahead and write this a little bit more cleanly. So we have a fraction of 3a squared times the square root of 3 over 8x. And I did something wrong again. Let's take a look. I see it. Okay, so that means this entire thing is going to be equal to 3a squared root 3 over 8x. Okay, that's the last example for this particular section. But now let's go on to something different. Simplifying radical expressions by rationalizing the denominator. Okay, let's go up and let's rationalizing the denominator. Okay, so the basic premise for this, I'm going to underline this because it's very important, is never leave radicals in the denominator. Never, ever, ever, ever leave radicals in the denominator. You get rid of them by rationalizing the denominator. So that obviously I'm about to show you what rationalizing a denominator is. Then let's go. The best way to show you what rationalizing it is to go straight into an example. So the thing is, we don't like radicals in the denominator because it's non-standard pretty much. If you're allowed to have radicals in the denominator, then you may have two different numbers that actually look different, but they're actually the same. And I'll show you that a little bit later, because otherwise a lot of people don't understand why this is important, but it's actually very important. So we say we have 6 over square root of 5. 6 over the square root of 5. You know what? Let's see if I can make this a little bit bigger. Ah, yeah, that's quite a bit bigger. Let's move it up a little bit too. So 6 times the square root of 5. We don't like this radical here. This square root is bad. So what is it that we can do with that? Well, we can multiply top and bottom by the square root of 5. So square root of 5 Okay, so notice that we're not changing the value of anything, because what we're doing is we're multiplying by 1. Remember, we did something similar to that before. So now we're going to be multiplying root 5 times root 5, and that's how we get rid of the radical, because root 5 times root 5 is just equal to 5. So let's go ahead and say that this is equal to the fraction of 6 times square root of 5 over 5. So this root 5 times this root 5 becomes normal 5, and then this 6 times root 5 equals 6 root 5. So now we've rationalized the denominator. We still have a radical, but it's on top. It's no longer on the bottom. The main point is this, to get rid of the radical on the bottom. Okay, so now let's go on to a pretty similar example. So say we have square root of square root of 7 over 3. So let's scroll down here. Square root of 7 over 3. Well, remember the quotient rule. We can say that this is equal to the square root of 7, the fraction of the square root of 7 over the square root of 3. So now we have, this is not considered to be good form, because whenever you have a fraction, the entire fraction is inside a radical, you can write it like this, so that means that there's a radical in the denominator. So this is bad form. So we want to go ahead and find a way to get rid of this radical. And whenever you do that, whenever you're trying to rationalize the denominator, see, the reason we call it rationalizing is because root 3 is an irrational number. So we want to make the denominator rational. So the way we want to do that in this case is we want to multiply the top and bottom of this by root 3. So whenever we're rationalizing the denominator, we always want to multiply top and bottom by whatever the radical is. If we had 4 root 3 here, we'd still multiply by multiply by root 3, not by 4 root 3. So this whole thing is equal to we're going to multiply this by the fraction of square root of 3 over square root of 3. Okay, so since we have the square root of 3 in the denominator here, we want to multiply top and bottom by the square root of 3. That means this will disappear. So now we rewrite this whole thing as the square root of 3 times the square root of 3 is going to be 3. But let's go ahead and type it out. So I'm going to have square root of 21 over 3. Okay, so root 3 times root 3 on the denominator becomes just 3, because square root of 3 times the square root of 3 equals 3. And then this square root of 7 times the square root of 3 is going to equal square root of 7 times 3, which is going to equal square root of 21. So now we've rationalized the denominator. So we have a rational number in the denominator because 3 is a rational number. Okay, so one more example, something pretty similar. Let's do 2 more examples because I have an idea for something else that we could do. Something that I just mentioned, but is not actually an example that we have yet. So let's say we have 1 over 2 root 2. Let's make it 3 root 2. Okay, so we have 1 over 3 root 2. Okay, just so you're not tempted to multiply top and bottom by the denominator, we don't want to do that. Instead, we want to multiply by this square root of 2. We only want to get rid of the denominator, we only want to get rid of the radical, not anything else in the denominator. So, let's multiply this by root 2 over root 2. Typing out fractions and square roots can be tedious in this. So we're multiplying top and bottom by square root of 2 over 2. And this then is going to be equal to square root of 2 over 3 times 4. Okay, so 1 times the square root of 2 becomes the square root of 2. But then this 3 times the square root of 2 times the square root of 2 becomes 3 times square root of 2 times... Gosh, that looks terrible, doesn't it? It's hard to write with the mouse. And this was something that I thought might be easier to write than to... Well, you can still tell what it is, though. It's 3 times the square root of 2 times the square root of 2. And, of course, these two together equal this. 3 times... You have the 3 here, and then the square root of 2 times the square root of 2 equals... No, not 4. I can't believe I just did that. It should be 2. Man, I'm glad I caught that. So, please note that this is square root of 2 times the square root of 2 equals 2, not 4. So, that means... Let's go ahead and clear this messy writing. So, man, I wouldn't have caught that either because I'm doing this... I'm making this up as I go along. I didn't realize that I'd messed that up. So, this, of course, can be simplified to 3 times 2 is 6. So we have square root of 2 over 6. So square root of 2 over 6 is the simplified form of this. And you know, this might seem like something that's arbitrary. You might think, why on earth do mathematicians care about radicals in the denominator? But this actually has a lot of application, and you'll see it if you go on to trigonometry. This isn't really an example, but if you go on to trigonometry, you'll see, like, if you have a number you'll see a lot in trigonometry is the square root of 2 over 2. Square root of 2 over 2. You'll see that a lot. And what if you say have if you're working on a problem and you know that the answer is supposed to be square root of 2 over 2, but instead you get 1 over square root of 2. And you know, you're racking your brain, you're trying to figure out why isn't this coming out the way it's supposed to. Well, the reason why is because 1 over the square root of 2 is actually equal to the square root of 2 over 2. See, since we have this standard, and let's go ahead and work that out. So we'd multiply top and bottom by square root of 2 times square root of 2. So we'll multiply top and bottom by square root of 2 over 2, and this is going to equal square root of 2 over 2. Because you have 1 times square root of 2 equals square root of 2, and then square root of 2 times the square root of 2 equals 2. So that means that these two things are actually equal. I just discovered today that I can draw on this, and I thought that was kind of cool. That's why I've been overusing it today. So square root of 2 over 2 is equal to 1 over square root of 2. And so that might seem like a strange standard, but it's actually really useful, because otherwise, you know, there's a lot of numbers that you would think are different when they're actually the same. Okay, so let's do one more example, and that example is going to be is going to be 1 over square root of 3x. 1 over the square root of 3x. So this is going to be, we want to get rid of this radical. Even though it's a radical times, even though x is in the radical, we still want to get rid of it. So how do we do that? Well, we go ahead and we multiply by square root of 3x. Okay, so square root of 3x times the square root of 3x, well, that's just going to equal 3x, but we're also going to have square root of 3x on the top. Okay, so we have 1 times the square root of 3x equals the square root of 3x, and root 3x times root 3x equals just 3x. So that is all the examples I have today. I will see you in the next lecture, which I believe is going to be section 8.4.